protons are made out of quarks that, as you told me, you apparently didn't do deep inelastic scattering in its full glory. Am I right by interpreting what you said the last time, 10 days ago? Well, let's see how much you remember, okay? The success of QCD, the very fact that we can have a theory of strong interaction, is based on the running of coupling constants we said. This is very important. That we can summarize at one loop level at least that the change of the coupling constant with energy or momentum exchange is given by this normalization group equation. This running is very strange, right? It's crawling. It's barely changing, okay? It's logarithmic, okay? But an euphemism. And we even know how to compute B, we said, it 11/3 times the gauge boson contribution minus 2/3 fermionic contribution minus 1/3 the scalar contribution, where these T's are defined as traces of the generator sphere, so they are functions of representation, right? And gauge bosons are, we know, gauge bosons are fixed for us. They are in the adjoint representation. We have no choice, right? That's a covariant derivative that teaches us. Fermions, we have a choice. But what we have seen in the standard model, they are either singlets or a fundamental representation, either of SU2 or SU3. So, in particular QCD, B3 for SU3, or sometimes BQCD, or sometimes B strong, written, we said must be 11/3. We computed this EGB, it was, we proved by induction that it's N for SUN. But if that proof escaped, you remember, we can do this by inspection. We know that the octet of SU3 is a triplet, ions plus a doublet, k ions plus another doublet, k bar, plus a singlet. This has a contribution too, I can do explicitly. This is a half, this is a half, this is a 0, so this is 3. The fermions are fundamental representation, left and right-handed quarks. So that means per each species there are 2 particles really, left-handed quark and right-handed quark. Each contributes a half. So I can write this as number of flavors, as we call them, number of fermions. And this is half of the number of generations, because in each generation there is 2 fermions, 2 flavors. Flavors, sorry, not fermions, because I count left and right separately. So this is 33 minus 2 and fermion over 3. Remember, we wrote this as 33 minus 4 number of generations over 3. When I write like this, I'm tacitly assuming that we are above the masses of all the generations. Because remember the rule in the randomization particles, the particles that run at energy bigger than that mass, they don't run. When they're heavy. Okay. This is what you have to accept at this point. But I presume a glimpse of that you got when you derived the randomization group equation. So just to give you B3 at the bottom mass, which is 4 point something GeV, is about 0.2. That was measured. See, this is sort of beginning to look good. This is already a bit small, right? It's a number less than 1. You can start we can, what do you mean? Alpha 3, B3. Alpha 3, I'm sorry. You measure that. Now you and I can go and check whether this really describes correctly the evolution of the QCD coupling constant, because people also measured it at MZ. Right? We got lab and we could measure everything at lab with high precision. We had 1 billion of these. And that was 0.118. But for example, from here I can compute alpha 3 minus 1 at MZ is alpha 3 at MB inverse, which is 5, plus, who is going to run between MB and MZ? Which flavors run? So who runs here? Or who doesn't? Well, top quark doesn't run, we said. The rule of the thumb is you don't run at the energies below, below your mass. You sort of decouple. So how many flavors am I going to have? So this formula is less useful than these formulas. Because when I'm in the region of sort of smaller energies where I'm below some of the particle masses, I can't use this formula, right? They're not all going to run. Okay, so let's not use it today. We may use it in the future when we want to study the evolution of the coupling constant QCD when we go to higher and higher energies. LHC, beyond LHC, okay, future collision. So so top quark is not running, so how many flavors do I have? 5. Up, down, charm, strange, and bottom. 5. So that's 10, right? So this is 23. I can just write like this, over 6 pi logarithm mc over mb. And you put the numbers, if you put the numbers, I think you get around 8.6. So you predict that alpha 3 of mz is roughly 0.12. I got it there. Which is pretty good agreement. We are at the 1 loop level here, maybe the 2 loop becomes important. Okay. That sort of makes you feel good. Now what happens if I go to lower energies? I want to do 2 things. I want to be able, now this is going to be easy, I want to be able to describe strong interactions with high energy. This is getting better and better, right? The coupling constant is perturbative here. Okay? At LHC even more perturbative. Now you can check easily. So let's go down from MB, let's do the following, to say GV. Suppose I can run in the other direction. Who is going to run from GV to MB? Well, B quark won't run. So in the beginning there'll be 3 flavors, but then immediately charm quark starts running around 0.5. So basically the particles that run here are U, D, S, and C. So there are less flavors. And you can do the same running. You find that alpha 3 of GV, let's do something like this, 500 MeV. You find that alpha 3 at 500 MeV is 1. Coupling is becoming strong. It's going to be bigger, right? When I'm going to lower energy. So you see what's going to happen? That there will be an energy, obviously. Let's go to lower energies even. There's going to be some energy that I can call lambda QCD, such that this is 0. You agree? All that is required that these are equal. And we can compute that. For example, who is going to run? This is below, you see lambda QCD. This is equivalent to saying that alpha 3 at lambda QCD is infinite. You know, we will see sort of confinement, we will see strong coupling. The coupling is We don't trust the infinity, of course, because we cannot trust this approximation. As the coupling is getting bigger and bigger, this naive calculation of perturbative expansion, of course, stops making sense. This is just sort of a hint that something dramatic is happening at that scale. And we can easily put the numbers here. Who is going to run between, okay, you will find out that that lambda QCD, no, here, is roughly 200 MeV. You will do that knowing that only up-down and strange quark are running. Chunk quark decouples, bottom quark decouples, top quark decoupled long ago. Okay, so lambda QCD is often defined, you will read in the book that it's 200 GeV. You need a more sophisticated definition of lambda QCD, not the one naively that I took here. But it's a rough, sort of here is just a rough kind of indication that when I go to below 500 MeV, the coupling is getting so strong that there is no sense anymore to talk of quarks and gluons and whatnot, right? We are getting strongly bound states that we call hadrons and mesons and so on, okay? So we can keep indicatively this. That's a number of 200 GeV. It's a little naive here. So what's happening at these low energies, right? How can we, you've heard that there was a Yukawa theory of strong interactions, right? You must have thought. By the way, if I use this from here, if this is the definition of lambda QCD, then often you will see this formula that alpha 3 of mu is, let's see, alpha 3 inverse of mu would be, from this formula, would be b over 2 pi logarithm mu over lambda QCD. Is defined in such a way that when mu, or energy, you will see often written as mu, I just want you to get used to that. This is energy that I use, okay? It can be an exchange momentum, maybe, a better thing, that a scale that defines the process. When mu is lambda QCD, I should get this here. So this is the formula that you will see very often. Or you will see that people write alpha 3 of mu is then, and B3 we said is 33 minus 2f over 3. Okay, we can then write the inverse of that. You may get it. You discussed Yukawa theory? That sort of people used to think of, and it seems to work, that strong force is exchanged at low energies of pions. The bigger the pions. Now, that looks a little crazy from our point of view. I mean, from our point of view, what is happening, right? I have a proton here, which is 3 quarks, and then quark is emitting a gluon. This is sort of a picture that you and I imagine. Well, I can draw it a little different for fun. I can draw it like this. It's still the same quark. The only thing here, give it an arrow. For this quark. This looks like a QQ bar system, you agree? Of course, if I have a 1 gluon, it will have a spin 1. But if I'm at low energies, there is no sense of talking of 1 gluon. The 2 gluons are equally probable, or 4 gluons, or 88 gluons. Right? The coupling is strong, so there is no perturbativity. But you see, this sort of, at low energies, it's not surprisingly having the possibility of an even number even dominating in a spin 0 combination. It sort of starts looking as if QQ bar is being exchanged, which is a meson. And if you are the energies which are below 200 MeV, already maybe below 500 MeV, for sure, only pions will dominate. It sort of, gives you an indication that this could happen, that this could work, but what you and I want, of course, is a fundamental theory, okay? This was just a kind of effective description that at low energies may not be so crazy. However, the task is to actually use the fundamental theory of QCD, and this is done on so-called lattice calculation that I won't talk about. I don't have much to say about, I don't know if I'm going to need it. Maybe just the thing is, you know, that the evidence keeps on accumulating that quarks look confined. Nobody has ever seen a free quark, and how that could work. If you take a meson, you know what we believe more and more, there is no analytic proof, is that what happens that the strong force is providing something that sort of keeps together, you know, a kind of string that, and here all the analogy that we had before with the weakly interacting theory like QED breaks down, or gravity at large distance, even the potential is 1 over r. What we expect is the potential to be proportional to r due to the strong coupling of gluons themselves. So imagine that you have a kind of strings keeping this guy together, and you try to pull them apart. What's going to happen? It's going to cost less energy to break the string. So what's going to happen is going to be something like this. This will be less costly as you keep pulling them apart. You will have to put more energy than to create another quark-anti-quark pair, which doesn't carry that much energy. Quarks are very light, remember? A few MeV. At the scale of which we are talking of the hundreds of MeV, they are critically massive. So we can keep imagining of never being able to break the binding, never being able to separate them. It's sort of, you know, believing that this picture, right, the dependence of alpha 3 as a function of energy or momentum exchange, we found out goes like this, it keeps falling down. Remember, this picture is naive. I could be wrong even here, because who tells me? So why did I erase it? It was 33 minus 2 number of flavors divided by 3. Flavors, actually, I should call them quarks or whatever. These are colored flavors. Only quarks count. But tomorrow we may discover more quarks. They may not be standard model-like particles. Let's not call them quarks, colored states, who knows. So eventually even this will break down. We have no reason to, we are very happy because up to the energies of 10 to the 3 GeV at the LHC, this works great, asymptotic freedom, okay. And it works all the way from practically GeV. We found out the coupling already getting less than 1. Now the thing is that you have to be sure that it will keep increasing and it become infinite when the energy goes to 0. This is good. And this is for the so-called lattice calculation, the idea of Kay and Wilson to use, to discretize space as a way of regulating these calculations, which are extremely hard. You first do computation for large spacing, which is easier, okay? I can't do justice to this extraordinary field. Okay, when there are only few lattice points, okay, you can do Monte Carlo simulation, what goes on. Then, of course, you have to keep increasing the number of points, or actually decreasing A, if you wish. And the great excitement of QCD, with added to the success of asymptotic freedom of coupling constant becoming smaller high energy, was the result in the late 70s by Mike Kreutz at Brookhaven National Lab, who was later on my colleague and friend, who showed that in an SU2 it was an approximate theory without fermions, even just that this self-coupling of gluons on the lattice seemed to give this absence of phase transition. Okay. And as we speak, there are more and more growing evidence that this is the QCD is a good theory of baryons and hadrons, but of mesons. But I won't talk about that. I couldn't talk with great authority or passion. It's very far from my expertise. What we can talk about, you and I, that's not so hard. It's what happens at higher energy. Okay, this is a field in itself. This will take a course to discuss. But we can feel good, right? We see it as we naively follow the coupling constant. It's getting bigger and bigger, okay? It's fairly indicative of what goes on. So why do you and I believe that protons and neutrons are made out of quarks? Now, the first evidence, I'm going to send you a picture. I got up late this morning, I didn't do it. I'm going to send you a picture of how the first sort of strong indication that something like this could be true, that you have this strange thing of quarks being almost free at high energies. Then when people did E plus E minus scattering at high energies, they found the things that we mentioned here, and you must have heard about. The production of jets of hadrons that will go back to back. So you get two jets, most of the time, back to back. These are jets of hadrons, a bunch, they go in bunches, pions, whatever, you know, other mesons. Very strange, as if you have a E plus E minus producing mu plus mu minus, as if you're producing 2 point-like particles that will go in the opposite direction, obviously. And by the way, the distribution that they got is the distribution that you get when you compute the cross-section. On E plus E minus going to E plus E minus, or mu plus E minus, okay. 1 plus cosine squared theta. And that's sort of a miracle, right? Why would this bunch of particles that should be scattered all around go as if you're producing, imagine that you are, this already gives you an idea, what if you're producing a pair of quarks and anti-quarks? Imagine the energy 100 times. When I say high energy, I mean large compared to the scale of QCD, of course, or at least much bigger. So they should be much bigger than proton mass to be on the safe side. Or strictly speaking, much bigger than lambda QCD, which is that magic number of 200 MeV, if we want to be more precise. So let's take the energy of 100 GeV. When I sent you a picture, which was LEP experiment showing this beautifully, these jets going back to back, what will happen if I produce these quarks at 100 GeV? Well, they're basically free. If I'm right that QCD is a good theory, okay, now you see we are sort of mixing the past and the present, okay. Then these guys, at this time, coupling big small, they come out as 3 quarks. At the time, which is roughly 1 over 100 GeV, which would be 10 to the minus 26 seconds. We found out the gene inverse was 10 to the minus 24 seconds, okay. Now what's going to happen? They start radiating gluons. Most of the time soft gluons, they start losing energy, right? Because the gluons will be emitted, just the way electrons emit photons. So they start being slowed down. Energy gets smaller and smaller for them. Eventually when they slow down to about GeV or less, what's going to happen? They're going to hadronize. But by that time they pick up their momentum. They already moved fast away from each other. And then it's sort of natural that the guys that are being produced, that are now produced with this huge momentum, will go back to back with the original distribution, okay? Because this is happening much later, okay? When the energy goes down to GeV, then alpha 3, or let's say 200 MeV, to be more precise, then alpha 3 of that energy, 200 MeV, is infinite very large and the hadronization starts, okay, I will get a picture like this. Objects going to bed. Now you and I know that alpha 3 at 100 GeV, although it is small, is not zero. So there is a good chance that occasionally we produce even a hard gluon that will pick up a lot of energy. So occasionally you should see 3 jets. I sent you a picture of that, which they see to a good degree. So that was the beginning of evidence. Okay, in other words, we are talking the evidence for 3 quarks, or evidence for quarks. So the first was this interesting behavior E plus E minus. But then, as you know, the true convincing evidence is the spectacular behavior of cross sections, okay, that I want to talk about a little bit. So let's try to do this calculation. I need your help. Okay? I don't know if you're sleepy. I was very sleepy, but once you start lecturing, you wake up. Once the teacher starts lecturing, the opposite effect takes place. But that's well known. And this is deep inelastic scattering. When I say deep inelastic, what I mean, when he started in the late 70s experimental slug with a fast moving electron hitting the proton. You want to be as fast as possible, right? You want large exchange momentum. If you're going to look inside the proton, the energy should be much bigger than the mass of the proton, obviously. That's how you will see things, okay? If I want to see what this is made of, right, I better smash it against the wall. The harder I smash it, the more pieces would come out, and I would see it better. It costs money, so you always have. No, it's similar, by the way. And it costs money, and you have serious debates. Are you going to invest money into doing that? You may learn a lot, but what if you don't learn enough? So what you do, in other words, let's imagine an electron coming in, emitting a photon, sorry, gamma, we exchange with momentum q. I have an electron, let's say that this momentum was k, this was k prime. Then what is q? That's k minus k prime square, which is k squared plus k prime squared minus 2k k prime. We are going to look, you and I, into q squared, which is, okay, let's go on. We want to have large q squared. Therefore, we are going to work in the approximation of electron mass being 0. I want to take you to the energies of 100 GeV. They started with the energies of 5 to 10 GeV. Still, even at that energy, this was small. So this is me square, right? So I can set it to 0. So this is minus 2k k prime. Notice that this is always negative. Let me write it actually. This is minus 2 et prime 1 minus cosine theta, where the theta is the scattering angle, right? If they are massless. You agree? Momentum is energy. So the only thing that will enter here is the production 1 minus cosine theta. You've seen this many times. So this is negative. This is often written as minus large capital Q square. This variable is used rather than Q square in most of the, not all of it, but in most of the calculation. Just to have more variables. I don't know. It's a pity in a sense because, but this is the variable that is used. So what is entering here is a proton with momentum p. Then when this q square is very large, what happens out? I don't know what happens. What comes out? It may be a big bunch of particles. What comes out with momentum p prime. Another variable which is very useful, is called nu, is p times q. And we want to work with Q square much bigger than MP squared, which I'm going to call capital M. And most of the time I'll be able to neglect it except when I can't, because it's in the denominator or whatever. So how would we compute this? See, there is a strong part, we have no idea how to compute, right? I mean, there is something, you know, we will start writing. What we will write, there will be a coupling E here. So there'll be E here. There'll be E, well, there'll be E. If I start writing, there'll be E here coming somehow, or whatever. Sure, it's going to be proportional to electric charge with some coefficient, okay. There will be 1 over Q squared for a proton propagator, you agree? There will be E bar K prime, gamma mu, E bar K, EK, sorry, times something that I could call mu, which I don't know what it is, right, if I wanted to compute the scattering amplitudes. So M squared is going to be something which is the square of this. In other words, I will have E to the 4th over Q to the 4th. I'm expecting. Then I will have to take the square of it. You know how to take this, right? And sum over spin. There will be a half. So in other words, there will be something, let me call it L mu nu, to indicate the lepton, the electron contribution, times mu star. What would L mu nu be? There will be 1/2 trace K slash gamma mu, K prime slash gamma mu. You have seen that. You don't have to worry about gamma mu and gamma nu, although this is symmetric mu nu, you would see immediately. There is no here, there is no parity violation, there is no epsilon mu nu term. Okay, this is QED, this is very simple. And this we've computed a number of times. This gives a factor of 4, so it becomes 2. K mu, let me see if you remember. K prime mu, it's symmetric, K nu, K prime mu, and then minus G mu nu, K prime. You remember this? Okay, let's leave it for the moment, okay? This is normally written. Let me get to the convention. I think with alpha squared. Right. Well, okay, in other words, maybe I could be a little more precise. I could write the d sigma cross section. Let me just remind you, there is a 1 over 4 k times p, the product of the regional momentum. I don't know if you remember this formula. Anyway, there is d3 k prime over 2 pi q 2e prime d3 p prime 2 pi q 2, let's call it EP prime, and then there is 2 pi to the 4th delta 4 p plus k minus p prime minus k prime times the amplitude m squared. Just to give you an idea, for example, this is invariant. So I can compute it in any frame that I like. I can compute it in fixed target space where I take proton at rest. So for example, in that frame, this is 4 EM. Mass would come out. Then there are these factors here. Let's at least write what d3k prime is. This is d omega prime, k prime square, dk prime over 2 pi cube 2e prime. Then there are these factors. I'm not going to integrate over p prime. I have no idea how to do the strong calculation part, okay? We are going to have to think a little bit, okay? So this is this privilege of the blackboard. Please take a little time. K prime is equal to E prime. Agree? So E prime cancels here. So in other words, the d sigma over d omega prime, d prime, there will be there will be charge to the force, e to the force. So the way this is defined is alpha to the force. Just to tell you, there will be alpha squared, sorry, q to the force. This is just a definition. Remember, I have q to the force, I have e to the force. So these are just the factors. Notice that there is e prime over e. L mu nu, W mu nu. So in other words, W mu nu is this combination normalized in some way, integrating over d3 prime and so on. You don't care so much, it's not so important what it is. When we integrate over these things, I'm going to call this W mu nu. I don't know how to compute this. You can imagine there's going to a little miracle come out if you bear with me, if you help me. So I try to look less at the notes. Now, what to say about W mu nu? In general, it's a function, you know, it's a mass. What you would say, well, W mu nu, you will tell me it will depend on P mu. P mu, it depends on P and Q. So there is P mu Q mu, there is C P mu Q mu, there is D Q mu Q mu. I don't know if then there is E epsilon mu nu alpha beta, P alpha Q beta. Did I take everything into account? I guess I did. In general, this will be. It's a function, W mu nu. It's a function of P and Q. I'm going to choose those variables. My initial momentum, and instead of working with P prime, I can work with P prime. I use Q as an exchange. It's the same thing. Remember, P prime is P plus Q. Here was Q squared. But there is no parity violation. Anyway, how do you know there is no parity violation? Well, look, this is symmetric. You don't even have to, you know, well, they shouldn't come out because there is no parity violation, but even if it did come out, you and I don't care because it will multiply L mu nu, which is symmetric, so it doesn't contribute. If this is symmetric, then B and C are equal. Only symmetric piece will contribute. Sorry, L mu nu is symmetric. So W mu nu only symmetric parts contribute. So instead of phi, I have 3 constants. But Q mu W mu nu must be 0. Conservation of current. Remember, it tells you that the amplitudes which you multiply with K mu vanish, with Q mu. and you find only two coefficients. W mu nu, it is written like this. Minus G mu nu plus Q mu Q nu over Q squared W1. It's just a way of writing. There is nothing here. And the other one is written as P mu. W2 and W1 have same dimensions, which I think is 1 over the mass. We can think about that, we don't care. So I have to divide it by m squared. I want them to have the same dimension. I'm sorry. Okay, you choose these particular two combinations. Why? Because then it's manifest that when I multiply with Q, I get 0. Okay, this is just, notice here immediately, here also. So, this is just you would determine relative A and B and D, sorry. So 2 would remain. These two, I don't know what they are. I have no way of computing it because of strong interactions. Well, there was no way of computing it today. We can try to imagine successfully applying QCD. Okay. At this point, what to do? Anyway, we multiply L mu nu I think I like the idea very more. If I don't give you a homework, and it seems that, okay, not all of you were here, except for Ahmed, who argued that number 8 is being given. It's better, but 7, you know, is a special number, so I'm not sure. Right?
I mean, but 50 divided by 7, that's more weight per whole. Or we can put 40% almost, it's fine.
That, you know, weight, saying, you know, it's a prime number. But anyway, Ahmed writes even numbers more. He said, well, another homework would be nice. You share that enthusiasm? No, I don't see that. Anyway, so then pay attention, then we'll include it in the, I think I'll put it on the final, okay? And it's not hard because this is actually given in the book, so just make sure that you will then follow the details, so at least get a glimpse of what I'm talking about. We'll fill in some of the details. So let's multiply L mu nu, aha. So this is what I need to make sense out of my X. I want to simplify this ugly form as much as I can to start seeing if I can find a way of understanding what is going on. It will have to do with the behavior of the structure functions of the proton. Notice that L mu nu notice that K prime is K minus Q. That's the definition of Q. So but Q acting on W gives me 0. So I can drop it. So at least I can write this a little more elegantly. This is actually 4K mu K nu minus, and notice that K prime is minus a half Q squared. Okay, so I write this becomes plus Q squared G mu nu. It's a bit simpler. And now we need to multiply L mu nu, W mu nu. Or maybe we'll take a little more space. Let me summarize it here. I will need at Q square, I will need it often 2kk prime. This is important. And there is a variable that I may use to simplify writing, which is P times Q. So what is L mu nu, W mu nu? It's noon. We could just give you the result, but at least outline how to get it. Okay, just to appreciate. For example, the first piece. So to multiply this with the W1 piece. So tell me what I get. I get 4k mu k nu minus g mu nu. This is minus 4k squared. Then q squared g mu nu minus this gives me minus 4 q squared. Then this piece times there is 4 k times q squared over q squared. And then there is a piece, this times the last one is q squared cancelled, just q squared. W1 plus W2 piece, let's do it later. You have this written, I'm gonna erase it. Okay, let's write the first piece only. Piece number 1. This is, notice that this is 0. Electron is massless. And k times q, I will need this. What is k times q? That's k times k minus k prime. So this is minus kk prime. So what is minus kk prime? This is q squared over 2. So this is minus 4q squared. This will become q squared. 2 and 2 cancels, do you see? Plus q squared W1. So it's minus 2 squared W1. It's quite simple. Piece number 2, a little more involved. What's a piece number 2? This times this. Okay, so I've, this we agree, right? So far, so good. What about this? It's 4k mu. K mu. So that gives me 4 k dot p minus p times q over q squared k times q squared. Am I right? I'm taking this piece times this. It's k times p, correct? Right? Yes. And it's going to be twice. Then there is a second piece, which is q squared g mu nu. So I can write it like q squared, I have that out. And what I have is p, I can write like this, minus p over q squared times q, everything squared. Or let me be correct, so that I don't lose you. P mu minus p over q squared, q mu. This is a bit messy.
W.
Ooh. Then there is W2 over m squared. Let's just catch what will happen. So there, I will get 2k dot p. I go inside with 4 minus minus 2. Okay, let's write it. K times Q, P times Q over Q squared. Squared plus Q squared. What is the here? I get P squared. I'm going to multiply this. P squared is M squared. You agree? Then there is off piece, which is P times Q squared, minus P times Q squared over Q squared times 2. I have 2 off terms, plus the last piece is the same. P times Q squared over Q squared. This is all multiplying W2 over M squared. Okay, but notice I have K times Q over Q squared. That's minus a half. No, a half. Right? 2K dot Q over Q squared is 1. So this is 1. These two disappear. What would you do next? Let's see if you can carry it a little more without being explicit. It got hard, right?
Why does the 2 cancel together?
Where? Here. I have
in the last term.
here minus 2 plus 1.
It's a minus.
It didn't cancel. It's just
It's
it's
a
the same term,
Yes, yes.
right? So the second piece well, at this point I would just substitute, okay? K dot P, did I write it somewhere? I go to the fixed target frame. So fixed target frame, proton at rest. Then K dot P is ME, K dot Q is P times Q is ME minus E prime. E and E prime are the energies of the electron. You agree? I'm at rest, so the energy of the proton is M, E, and E prime. So look, this piece is, so number 2, what I get here, the first piece is 2ME minus P times Q is minus E prime M. Square plus Q square M square q square m square is minus okay, the second piece, there is q square m square. Maybe I should have written minus p times q square. I should have substituted maybe immediately. Anyway. W2 over m square. And this is what? This is m square e plus e prime square. Plus m square again is common here. Q square I computed, I commented this is minus 2 2k prime minus 2 e prime. Minus 2 e prime 1 minus cosine theta minus, what is p times q? Where is it? M e prime minus m square I took out e minus e prime square. W2 over m square. M square cancelled. Maybe I'm okay. If I don't get it right, we'll just copy the result. But let's see. So what is this? This is e square plus 2 e prime plus e prime square minus e square minus e prime square. I'm substituting this.
Yes.
So it becomes plus 2 e prime minus 2 e prime 1 minus cosine theta W2 e square e prime square. So I have 4 e prime minus 2 e prime. So this becomes 2 e prime is common 1 plus cosine theta W2. This is the second piece. 2 is this. The first piece, let's just summarize it here. Can I raise this or you're still on it? This line here. Let me write this nicer. 2 is equal 2 e prime 1 plus cosine theta. And this is equal 4 e prime 1 minus cosine theta W1 W2. This is the second piece and this is the first piece. Remember, this was the definition of the cross-section, where q squared is minus 2 E prime, but I'm using 1 minus cosine theta, which I wrote as 4 E prime sine squared theta over 2. And 1 plus cosine theta I wrote as 2 cosine squared theta over 2. Right, 1 minus cosine theta is sine, 2 sine squared theta, 1 plus cosine theta here. This is 2 cosine squared theta over 2. So in other words, this becomes, and this thing here, okay, it's there, sorry, it's up there. So q squared, q to the fourth, in other words, q to the fourth is going to be d square. So what we get, d sigma, this is what you can measure. Okay, we found a reasonably neat expression. There was E prime, and another E prime is E prime square. But we have here 4, so we get 4 E square sine square, no, sine to the fourth theta over 2. 4, here there is 16. And then there is 2W1 sine squared theta over 2 plus W2 cosine squared theta over 2. Okay, this is the celebrated expression for the deep inelastic scattering of electron and a proton. Now notice a strange thing, there is a tremendous singularity in theta going to 0, right? Of course, you expect more events with you. It's more likely that this guy will just go through, right? It's not easy to reflect. But the singularity like this, well, remember I took m equal to 0.
Yes.
So there is no real singularity, okay? This is valid for theta above some small angle, okay, which probably is ME over energy or whatever, okay. And this is typical when you get E plus E minus or mu plus mu minus, even Rutherford scattering is this, if you remember Rutherford scattering formula, Rutherford formula had this thing, okay. This is just telling you that it's more likely to go through, but it's also telling you what Rutherford found quite exciting, and the rest is history, we can say, that even a large angle happens frequently, right? In the case of Rutherford, it was a great thing. This is we wouldn't expect that if an atom was a sort of a pudding, you know, that I mentioned that pudding. So now you see what you could do now, and it's a mess. Imagine the experimentalists, you're going to measure these functions, and they are going to be functions of two variables, q squared. There are two variables, there is p prime. You could use p squared, but that's m squared. So what you need, two independent variables, the ones that we have chosen, q squared and nu. Nu was p times q. And q squared is minus q squared. These are the variables used. What I saw was quite surprising, but what I saw is what they could see was actually something they were told to look for by Bjorken, who was with Feynman somewhat before, started to see what would happen if quarks were free. In other words, what they're going to find out that it's precisely not these functions. They're going to normalize them a little differently. But more or less, they will find out that these guys, instead of depending on these two variables, they depend only on the ratio of the two variables. Very surprising. Okay, there is it's called a scaling variable x, which is defined as q squared over 2e. Basically these w's, but I'm going to normalize them a little differently, we'll see in the moment, are functions only of x. Very strange result. Consistently a different q squares. Okay. That will be very surprising. Okay, so what we should do, briefly, show you how it emerges from the, what they call the parton model, which is what will happen. Feynman was looking into it. What will happen, and you can, if you would imagine the quark to made of 3 partons, Feynman called them. I think Feynman, people say that he wanted to be objective. I'm not so sure. There was a tremendous competition, friendly competition between him and Gell-Mann. You know, 2 geniuses working together. You can imagine. And Gell-Mann used to be very, very upset when people called them partons. You know, he says, "You mean quarks?" He would tell me, you know, people we would read these anecdotes. I think Feynman was maybe doing it to spite. You know, quark model function nicely. Well, of course, you can tell me it function nicely as a bookkeeping at low energies. Why would you imagine that it's going to work at high energies? Well, why not try that? Anyway, and actually they did, because the first calculation, the series calculations were done. We are going to assume that partons carry spin half. That's a quark. So let's look at the parton picture, which is a quark, which is a spin half fermion. In other words, we are going to assume that proton is made of these 3 partons. And just see what happens when I scatter an electron on a quark. So we are going to look at the electron plus quark going into E plus quark scattering. In other words, but we are going to say that this quark, okay, the picture changes. I simply have, so there is exchange momentum Q and also Q for the quark. So let's call it a part, but P is also momentum. You see, notation becomes messy here. So there is a quark. This quark, or parton, has some charge. Another problem notation, Q, let's call the charge of our parton. The notation QQ would be the charge of Q, where you ran out of... The thing is that this quark is going to have the momentum. That's the only thing we have, the P of that quark. Let's put P hat. Is some C times P. In other words, you will assume that this guy is carrying a fraction of proton momentum. Very reasonable, right? Tendentially, he's moving along with the proton. I have a fast-moving proton. I have very high energies. Okay, I can do that. I can also go to the rest frame. But if they move, I will in the frame where they move, in the center of mass frame, I will assume that this guy carries a fraction. And I'm not assuming anything about that fraction, okay? That's a reasonable thing. So what happens is, okay, so what will be the amplitude square? That's going to be E square times E square e to the 4th, Q parton square, or sorry, Q to the 4th, exchange of 1 over Q square, you agree? And there will be this thing that I will call L mu nu times, to keep you suffering, Q mu nu. Now this is a point-like particle, so this is basically the same expression as the one we had before. So just to help you, Q mu nu will be what? Will be 2, there was a factor of 2. Right. C P mu, P prime mu. I'm not assuming anything about the momentum P prime. I know what it is, and I'm going to use it. It will be useful. It's P plus Cp plus q plus p mu, no, Cp nu p mu prime plus 1/2 q square g mu nu. That product was 1/2 q squared. Okay, before I multiply them, let me just say I'm going to have to integrate, remember, over d3p prime over 2 pi cube to pp prime. Remember? This I can write as integral over d4p prime over 2 pi cube times delta p prime squared. Let me see if you see that immediately, or I have to remind it. You often use tricks like this, I'm sure. But after all, the delta function of this is one of the two derivatives, which is just the absolute value comes from the and we have to do the integral. There is also then of course there was an integral of 2 pi to the 4th, you agree, delta p prime minus Cp minus q delta 4. We had this. We have to do integral like this, right? When we do the cross section there was k, but this was a thing that we had to calculate. We couldn't do that in the case when I assumed that proton was a proton, a strongly coupled fuzzy thing, right? So I had to do this trick of reducing the structure functions. Here we can do the integration. So when we integrate over p prime, notice that we can do the integrator over p prime is trivial. Right? The 3 momentum is trivial. And the p0 prime will give me, so this is going to give me this integral. It give me delta of p prime square, but that's Cp plus q square m square, doing this integration. Okay. Oh, by the way, another important assumption, I will assume that quarks are massless. Quarks have very little mass. This is very important for our calculation. In order to get a neat expression, I'm going to assume that of course is well justified. We know that quark masses are small. But this is just an assumption. So in other words, p square is 0. Okay. I can use p square equal p prime square is 0. So this is delta 2 Cp times q plus q square. I will write minus q square times amplitude. This is sort of to write average m square. Okay. This is equal 1 over 2 p times q delta c minus q square over 2 p times q, which I call nu. This I call x. Remember, this is a famous variable of scaling. So we got here. So I can also write this as x over q square. It's the same thing because of the delta function. Delta psi minus x. we learned something interesting, that is this interesting variable is just a fraction of the momentum that the quark is carrying when it's scattered. And now we can do the calculation. And I think I should leave it to you, it's getting late, and let's put the bits and pieces together. What we get is, we'll get it as B sigma, B E prime, D omega prime is E prime over M E Q squared. Let me indicate the factors. Delta C minus X No, I have to do something more. I'm sorry. I forgot. We didn't compute L mu nu times Q mu. I just forgot to do that. L mu nu times Q nu is there was 4 K mu K nu plus Q squared G mu nu. Had to multiply, and what is this guy? Well, actually, before doing that, I can do something better. Sorry, I don't have to do that. I can do something better. Q mu nu is, no, let's just write down what Q mu nu is. You will see this is going to be, Q mu nu is, C is equal to X. So it's 2 X P mu P nu plus, no, X P nu plus Q mu keep it like this, plus P nu X P mu plus Q nu this is equal to X squared P mu no. No, let me keep this plus Q squared G mu nu. I have added here minus what have I added here? I have like half that is bugging me. See what I'm doing? Are you still I've added Q mu Q nu over X squared. But why is it a half? I've somehow,
But there's a 2 outside.
2 was here outside. Ah, it's like this.
Yeah.
So it's this. Or not, I'm not sure. Notice, what is 2x? That's minus p over q squared. if you look at the definition. So I'm recovering the form that we had, and by the way, this I will write as q squared g mu nu minus q mu q nu over q squared, which is q squared minus g mu nu plus q mu q nu over q squared. If you look back at this definition, we can read off immediately what W1 and W2 are. I got a form. In other words, this is the form for a form for the for W mu nu precisely. So what we should read from there, let's, I think, wrap it up. Well, let's see if you have followed it up. Remember that there was 1 over q squared here. Came up when I integrate over p prime. I had this 1 over q squared. So from here you find out, please when you check, the W1, all we have to is to normalize it. It's 1, I think we get 1 over 2 q squared there should be m over, there will be, sorry, there is no q squared will cancel with 1 over q squared, so it's going to be qp squared over 2m. This is what comes out, delta c minus x, and W2 is x m over nu comes out factor of 2, where once again I have used the fact that 2x x was q squared over 2 nu. I use it here. This is what I do. Please try to see it, okay? We'll include it the this is one way or another to have you do it. There is also qp squared. So what people introduce, there was a particular combination of these two one. You multiply this is W1 is m W1 W1 tilde, which is qp squared over 2 delta c minus x. W2 tilde is nu over m W2. You will see why they are a little more convenient. This is qp squared times x delta c minus x. This is what we got. See, we now have W1, W2, one gets the usual scattering. So, there is a fundamental prediction. You can write it now in terms of W1 and W2, but what is done traditionally is this. Prediction that W2 of x is 2x W1 of x, and it's 1/2 qp squared delta c minus x. This is what was measured. This is what they found. they would have never seen it. They were told to look for it. Imagine that you really, first to introduce the right variable, it's already something very trivial. This you wouldn't have noticed if you use W1 and W2. You have to do the proper normalization that told you that actually quarks behave as if they're made out of, the proton behaves as if it's made out of 3 quarks. These people then studied to change Q square, and we can say the rest is history. Of course, the true history is that eventually people learned to do the perturbation theory of QCD once the asymptotic freedom was established. So what you do these days, you of course, you do the QCD contribution, quarks are not free, and the agreement gets better and better and better. But the striking thing is here, okay? This is how the original belief in quarks emerge. This is how we see them, if you wish. Okay? You see sort of the definition of seeing as we go along, there's sort of a problem of growing up, you know, it gets redefined all the time. First you see with the naked eye, then you see, oh, okay, I can use a lens, or you say, well, you know, to use a microscope, I can use a Wilson chamber and so on, and see the trace of the particle. What we see here is quite indirect. We never isolated a quark, but we get better and better agreement of quarks. So what really is that this W2 over X, which is QP squared, it's sum over QY squared inside the proton times a probability that that guy carries a fraction of momentum x. Okay, this becomes a true thing to do. Maybe it's getting late. I'll just say a few words next time about these so-called structure functions. And I send you a picture. So